as we discussed a while ago, that since we can't visualize four-dimensional data sets, there has to be some way for us to visualize our data set, which has four features, which is sepal length, sepal width, petal length, and petal width. It's a four-dimensional data, and since we can't do four-dimensional scatter plots, there has to be some hack, there has to be some smart way of visualizing all of this data at once. So one such interesting way of doing it is called pair plot. As the name suggests, we actually do pairs. So the one pair that you saw is a plot between sepal length and sepal width a while ago, right? How many such pairs exist? Since you have four variables and you're trying to create pairs of two, you can have 4C2 number of pair plots. So this is a plot where you have a two-dimensional plot between two variables can be thought of as one plot. And how many such plots can you have? You can have 6 such plots, right? You can have a plot between sepal length, sepal width. You can have a plot between sepal length and petal length, sepal length and petal width. Similarly, you can have a plot between sepal width and sepal length is already taken care. Sepal width and petal length, right? You can have a plot between sepal width and petal width, and you can have a plot between petal length and petal width, right? So these are the 6 plots that you can have. Of course, I didn't write sepal length and sepal width because once you have this plot, this has x-axis and this has y-axis, or vice versa, the other plot is straightforward. So you have 6 unique plots that you can plot. And when you visualize the 6 plots, you get a sense of what the data is in 4 dimensions. So this is the hack we're going to do. So instead of visualizing the 4-dimensional scatter plot, which we cannot, we are going to visualize 6 two-dimensional plots to understand what the data is. And such a plot is called a pair plot. So let's go and look up how the pair plot looks like. So this is what, so if you just run a very simple command in Seaborn called pair plot, you just say sns.pairplot and you give it iris. This is the data set that we are running it on. Color it by the species label, and you're just putting a size to your whole plot, right? As soon as you do this, what we get here is a plot like this. Now let's digest what this plot is. First and foremost, the legend here. Your blue points are setosa, your orange points are versicolor, green points are virginica. That's the first thing, okay? And now what you see here is, you see basically a matrix of plots, right? This is the first row, this is the first column. Please ignore for now all these diagonal elements. So these 4 elements are called the diagonal elements. These 4 plots that you're seeing here, let's just ignore them for a second. We'll revisit them when we learn about histograms and PDFs and CDFs. We'll come back to these plots. So for now, just ignore these diagonal elements. Let's look at all the non-diagonal elements. The first row, for the first row in this matrix of plots, the y-axis is always sepal length, as denoted here, right? Now your question is, what about the first column, right? For the second row, this is sepal width. So since it's mentioned here that it's sepal width, neglect this for a while, just ignore this for a while, ignore these. This is also sepal width and this is also sepal width. So whatever you see here corresponds to the y-axis of all the plots in that row. What about the columns? Now, if you go slightly down, you will quickly notice that all these values are given here. So you have sepal length here, which means in this column, the x-axis for all the plots is sepal length. So this is sepal length, this is sepal length, and so on and so forth. The second one is sepal width. So this x-axis is sepal width, this x-axis is sepal width, and so on and so forth. So all the column x-axis labels are given at the bottom, and all the row y-axis are given on the left here, right? So if you pick a plot like this, it doesn't have any x-axis and y-axis, but we can look at this row and we say, okay, this is sepal length. We can quickly look at this row and say, this is sepal length. And what about this column? Let's go down and see. This column corresponds to petal length, which means this plot will have its x-axis as petal length, right? Simple. And I told you that we have 6 plots, but if you count here, if you ignore the diagonal elements, you see 12 plots here, right? If you see, you have 1, 2, 3, 4, 5, 6 above the diagonal. These are called above the diagonal plots. And you see 6 plots here, 1, 2, 3, 4, 5, 6. But if you notice carefully, they're just mirror images of each other. Let's take these 2 plots, right? This plot, the x-axis is petal length, the y-axis is petal width. For this plot, the y-axis is petal length and the x-axis is petal width. So what we have just done is we have made our x-axis here in this plot, y-axis in this plot. You've made the y-axis here as x-axis, except that these two plots are exactly the same, more or less exactly the same. So the lesson that you learn from this plot will be same as the intuition and lessons that you learn from this plot. So we will just focus on the top 6 diagonal matrices, right? So these 6 matrices. Let me just zoom out a little. And okay. Okay, so these are the 6 plots that we'll plot, that we'll dive into a little more, because the other 6 are exactly mirror images of this, right? So here is your sepal length versus sepal width. As we have learned earlier, your setosa flowers can be well separated from your non-setosa flowers by drawing a line like this. This was what we saw a little earlier, right, when we were learning about 2D scatter plots. But the moment I go to sepal length and petal length, wow, this is better. Now, if you look at this plot, your setosa flowers are much more well separated from the rest of the flowers. So the first takeaway from a plot like this is petal length, right? The x-axis here is petal length, right? The x-axis being petal length. So if I draw a line like this, I can separate my setosa flowers from non-setosa flowers very, very easily if I'm using petal length as the axis on which I'm separating it. Similarly, petal width. So here the x-axis is petal width. The y-axis still remains sepal length. Even in petal width, my setosa flowers are very well separable from my non-setosa flowers, right? So the first takeaway is the petal length, because the x-axis here is petal length, the x-axis here is petal width. So the first takeaway is petal width and petal length are able to separate my flowers much better than my sepal length and sepal width. So why don't we go and focus and look at these data points, look at these plots where for example, if you take this plot, right? So if you take this plot has this corner plot here has petal width on the x-axis and petal length on the y-axis. Now this is super good if you look at it, because this is okay. Let's number them. This is 1, this is 2, this is 3, 4, 5, 6, 7. And what about the x-axis? Let's just go a little down and understand what the x-axis is. 1, 2. Okay, perfect. Let me realign my stuff here. Okay. So my x-axis here is petal length, and this is a value of 1, value of 2, and value of 3 somewhere here. Okay. Now by looking at this plot, which is a plot between petal length and petal width, wow, my setosa is much well separated. See, it's very far away from the other two plots, from the other two flowers. It's significantly separated. So what if, instead of drawing lines and all of that, we use the if-else conditions that we all know in programming? Now, if you want me to build a model right here, I can build a very simple model to separate my 3 types of flowers. Let's do it right now. It's very simple. By just looking at pair plot like this, I can quickly write a simple model. What if I say that if petal length, so because this is petal length, right? This is my petal length. If petal length is less than equal to 2, which means everything below this line, right? And if petal width is less than equal to 1, which means everything below this line, which means what I'm talking about is this box, right? Because all the points in this box will have because this is petal width, right? Petal width less than 1 is this region. Petal length less than 1 is this region. So if my petal length is less than equal to 2, because this is 2 and this is 1, and this is 1 and this is 0 and this is 1 for petal width. So if my petal length is less than equal to 2, and if my petal width is also less than 1, then my flower type is setosa. Look here, using a very simple statement like if else and a boolean and, we simply built a model to separate setosa from everything else, right? Since we have separated setosa, now let's look at your versicolor and virginica. Now here what I can say here is this. So this is a value of 1, value of 2, this is a value of 1, 2, 3, 4, and 5, right? So we said, and this is your petal length and this is your petal width. For setosa, we wrote a very simple rule that your petal width has to be less than 1. Sorry, this is 1, This is 2, sorry, that's a typo there. 4, 5, and 6. And we said your petal length has to be less than 2, which means this box, this region is your setosa. What about your versicolor? Your versicolor mostly points lie between this region and this region. Right? Of course, there are some green points here, but that's okay. We will make some mistakes. Machine learning is never perfect. And if you look at, if I have to draw a bounding box around it, I will say I can draw a bounding box like this, right? So now let's try to put this into a simple rule. So we can say if petal width is less than equal to 2, right? Or we can just strictly say less than 2, which means this part, because petal width is this, petal width is less than 2, and petal width is greater than equal to 1, which means this region. So what we are doing here is, so you can think of this line as saying petal width greater than 1. You can think of this line as saying petal width less than 2. So by boxing these two, you're getting this whole region, right? You're getting these two lines. Now what about these two lines? You can say, and if petal length is less than 5, petal length less than 5 is this part, corresponds to this line, right? So this whole region is petal length less than 5. And if petal length is greater than, and if petal length is greater than, let's say 2.5, because this line is about 2.5, right? So if you do a Boolean AND of these 4 conditions, then you can say, then it is versicolor. Right? Of course, you're going to get a few of these green points which are misclassified as versicolor. While they're virginica, you're calling them versicolor. That error will be there, because if you look at it, even in the space of petal length and petal width, your orange points which correspond to versicolor and your green points which correspond to virginica are not fully separable, right? So what we learned from this simple discussion is that using simple if-else conditions and looking at pair plot. See, by just looking at the pair plot, I quickly realized that petal length and petal width are the important features to distinguish these 3 types of flowers, and I wrote a very simple if-else condition. So by just simply drawing your pair plot, you've built a very simple model which works reasonably well. Of course, it's going to make mistakes whenever it sees it's going to make mistakes for points like this, but that's okay. Machine learning is never perfect. You will make errors. Okay, so what we've learned is pair plot is extremely important. So I've written my conclusions and my observations here. All that I'm saying here is petal length and petal width are the most useful features to identify various flower types. While setosa can be easily identified, virginica and versicolor have some overlap, and we can just do simple if-else conditions to separate these types of flowers. So congratulations, you built your first very simple model to separate these 3 types of flowers. Using simple pair plot, nothing more fancier than that. It's a very, very simple tool.